Welcome to the deep dive. We're here to take really dense, cutting-edge research papers, the kind that takes serious time to digest, and pull out the core architectural insights for you. The goal is you walk away understanding the key ideas right away. Today, we are diving deep into a paper called PokeeResearch, Effective Deep Research via Reinforcement Learning from AI Feedback and Robust Reasoning Scaffold. And we're going to focus laser-like on the methodology and the results. This is really for those of you out there who are, grappling with building deep research agents that are not just capable, but actually stable and reliable. So let's set the stage a bit. Tool-augmented LLMs are everywhere now. The promise is they act as these autonomous research agents, take a complex question, break it down, go find evidence, synthesize it, give you a grounded answer. It's the dream, right? The full cognitive loop.
It is the dream. But as the PokeeResearch team rightly points out, current agents often fall short. There are really three big areas where they struggle. First, retrieval. It's often just too shallow. The agent can't really handle queries that need complex, multi-step information gathering. It gets stuck on simple searches. Second problem, and this one's huge, is weak alignment metrics. So many systems still lean on things like F1 or AnyG, basically token overlap.
Right, just counting words.
Exactly. And the problem is, those scores can look great even when the answer is factually completely wrong. You share a lot of words, you get a high score, but the meaning is lost. It's a poor proxy for truth.
And the third one, this is the one that I think drives engineers crazy. It's just how brittle tool use can be.
Oh, absolutely. Think about it in practice. Your agent makes one slightly wrong API call, or maybe the search tool hiccups for a second.
The whole thing just crashes.
Precisely. The whole research path just collapses. Older systems, they don't have that built-in ability to say, okay, that didn't work. Let me try rephrasing that query, or let me try a different angle. They just fail. Stop.
Okay, so this paper proposes a solution, PokeeResearch 7B. It's a 7 billion parameter agent built on Qwen 2.5 7B Instruct. But the key thing is this unified reinforcement learning framework they've designed specifically to tackle that brittleness and that alignment problem. They're aiming for something reliable and, importantly, cost-efficient at that 7B scale.
And the way they achieve that resilience is really what we need to unpack. There are three core innovations working together here. First, there's the training pipeline itself. It's driven by human values, but implemented using reinforcement learning from AI feedback, RLAF. And crucially, they use a specific algorithm called Reinforce Leave One Out, or RLAO. Second is what they call the robust reasoning scaffold. Think of it like architectural guardrails. It provides stability at runtime through things like self-correction when things go wrong, explicit self-verification before giving an answer, and the ability to handle multi-call reasoning.
Okay, RLAF with RLOO, the reasoning scaffold, and the third piece.
The third piece is something they use at test time, mainly for the really tough problems. It's called Research Threads Synthesis, or RTS. It's basically a strategy for dealing with situations where different lines of inquiry lead to conflicting answers.
Got it. So we've got the big picture. Let's dive into the mechanics now, starting with how this agent actually operates day to day, or rather query to query. This research verification cycle you mentioned, it sounds like a big shift from just generating an answer and calling it done.
It really is. It's fundamental to the agent's resilience. You can think of its operation as switching between two modes. The first is research mode. This is where the digging happens. It's multi-turn, step by step. In each step, the agent has a choice. Either issue a tool call, rep in these tool call tags to go get more info.
Like hitting the search engine or reading a page.
Exactly. Or, if it thinks it has enough, provide a synthesized answer marked with answer tags. Now here's where that self-correction comes in, baked right into this mode. Let's say it issues a tool call and it fails. Maybe the query was badly formed, maybe the network timed out, maybe the search just found nothing relevant. The agent doesn't just give up.
Unlike older systems.
Right. It stays in research mode. It recognizes the failure, and it can maybe tweak the query, try a different tool parameter, whatever it needs, until it either gets some useful evidence or it hits a turn limit they've set. That adaptiveness is key to overcoming brittleness. Only once it generates an answer does it switch modes.
And that takes us into verification mode. So this is like the agent stepping back and reviewing its own work.
Precisely. It does this exhaustive self-check. It looks at the entire history for that query, the initial question, all the tool calls it made, the snippets it got back, the answer it just generated, and its only job in this mode is to decide, is this answer actually correct, factually sound, and does it fully address the original question?
And if it decides, yes, this looks good,
then the thread terminates. Success.
Mm.
But if it finds a flaw, Maybe it missed part of the question. Maybe the evidence was weaker than it thought when generating. Maybe there's a simple logical slip-up. It flags the answer as incorrect and pops right back into research mode.
So it forces a refinement loop. It has to go back and fix the specific problem it identified.
Exactly. This directly tackles what the paper calls the generation verification gap. It's this known issue where an LLM might be good enough to generate something that sounds plausible.
But not critical enough during generation to catch its own subtle errors.
Right. But when it switches to verification mode, it can look at the whole static log and apply that critical lens much more effectively. It's easier to spot errors when you're reviewing than when you're creating under pressure, essentially. And they explicitly designed this verification step to catch 3 really common critical failure types. First, the incomplete answer you asked for A, B, and C, and it only gave you A and B. Second, hallucinating an answer when the evidence just isn't there. The agent might generate something, but in verification it realizes, hang on, the docs didn't really support that. And third, those simple, logical mistakes within the reasoning chain that are easy to miss during generation, but obvious on review.
Okay, that makes sense. Now, to do all this research, it needs tools. What specific tools does PokeeResearch 7b have access to? You mentioned a couple.
Yeah, they kept it focused, mirroring how a human might research. 2 main external tools. First is a web searching tool using the SERPer API. It takes a list of search queries, strings, and gets back structured results. URLs, snippets, the usual search stuff. This is for that initial discovery phase, mapping out what's available. Then there's the web reading tool powered by JanaReader. This takes a list of URLs found by the search tool and gives back a concise summary of the content on each page. This is really important for efficiency.
So it doesn't have to process the entire raw HTML of every page.
Exactly. It gets the gist first, decides if it's relevant, then maybe dives deeper if needed. It saves a lot of time and compute tokens. It's a smart filtering step.
And quickly on the training data, they use something called MirrorRL Gen QA. You mentioned it's known for complex questions.
Yes, it's a data set specifically designed with these tricky, multi-turn question-answer pairs. The key thing for us is that they were careful not to use any data from the benchmark datasets they eventually tested on. This ensures the evaluation is fair, and the agent isn't just memorizing answers. It learned the process on hard, distinct problems.
All right, let's shift gears now to the real technical core, that unified RL framework. You highlighted RLAVE with reinforced leave one out, RLU. Why RLU? Why not stick with something more common like PPO, which we see in a lot of agent training? What's the big advantage here for ML experts listening?
Yeah, this is crucial. It really comes down to stability and bias. When you're training an agent to use tools, the environment is complex, the rewards can be really sparse. You either succeed or fail, often with little in between and very noisy. Algorithms like PPO or even many RLAI variants are technically approximately on policy. They introduce biases in how they estimate the policy gradient to improve sample efficiency.
But that bias can be a problem.
It can be a huge problem when your rewards are sparse and noisy. Those biases can get amplified, leading the policy astray, causing instability, sometimes even catastrophic forgetting during training. RLOO, on the other hand, draws on some solid theoretical work in policy optimization. It's a true on-policy method, and its main advantage is delivering an unbiased estimate of the policy gradient.
Okay, unbiased. How does it achieve that? Let's get into the mechanism a bit. You mentioned this leave one out baseline. How does that work mathematically to get rid of the bias and maybe lower the variance?
Right, so imagine for a given prompt, let's call it $6, the RLOO algorithm samples a small batch of, say, different possible completions or trajectories. These are all generated using the current policy. For each completion, you get a reward, probably from your AI judge. Now, the key is the baseline, $. For any specific sample, its baseline dollar is calculated as the average reward of all the other K1 samples in that same batch. So $Y for going K1 some each day.
Okay. So instead of comparing it to some global average or a learned value function, which might be inaccurate, you're comparing it directly to how its peers performed on the exact same prompt in that exact same batch.
Exactly. It's a very localized, contemporaneous comparison. This lets you calculate the advantage, AI, simply as the difference. AI equals RXYA. And because that baseline $B was calculated without using AI, it's mathematically independent of it. That independence is what guarantees the gradient estimate derived from this advantage is unbiased.
And you mentioned lower variance, too.
Yes, because you're effectively centering the rewards within that small batch. Any weirdness or noise that affects all completions for that specific prompt gets subtracted out by the baseline. It removes prompt-level constant shifts in the reward signal, which dramatically reduces the variance of the gradient estimate, leading to more stable learning.
That sounds pretty elegant. But how does it stack up against other methods that also use relative rewards, like group relative policy optimization, GRPO? The paper apparently contrasts them directly.
They do, and it's an important comparison because GRPO is another relatively recent approach trying to tackle similar problems. The PokeeResearch paper argues that GRPO makes a few compromises that ultimately hurt stability compared to RLO. First, GRPO calculates its baseline using the mean of all the rewards in the group, including the sample being evaluated. Mathematically, this introduces a small but definite bias into the advantage estimate right from the start.
Okay, so step one, it's already slightly biased where RLO is not.
Correct. But the second point they make is maybe even more critical, especially for training stability. GRPO performs a normalization step. It divides the advantage it calculates by the standard deviation of the rewards within that group. Normalization often sounds like a good idea, but here they argue it results in a biased parameter update overall.
How does dividing by the standard deviation introduce bias?
Because it changes the scale of the update based on how variable the rewards are in that batch. If rewards happen to be very volatile, high standard deviation, the update gets shrunk, potentially slowing learning on critical gradients. If rewards are very consistent, low standard deviation, the update gets magnified. This means the policy updates are skewed by the variance of the rewards, not just their mean difference, which RLO avoids. And the third point is that GRPO typically uses PPO-style update mechanisms, things like clipping, running multiple updates per batch of data, KL regularization. All these tricks mean GRPO is still fundamentally and approximately on-policy algorithm, not truly on-policy like RLOO.
So what did the PokeeResearch team actually find when they compared them head-to-head in practice? Did RLO live up to the theoretical promise of stability?
This is where it gets really interesting. They reported that the standard deviation normalization used in GRPO frequently led to what they called performance collapsing, especially during longer training runs.
Collapsing, like the performance just flatlines.
Worse than flatlining. It means after some initial progress, the policy's performance could suddenly and rapidly degrade, sometimes becoming unusable. It seems the policy gets destabilized by those biased, variance-scaled updates and essentially over-optimizes in the wrong direction, losing its ability to generalize. RLOO, in contrast, showed much more stable and consistent progress throughout training. So that empirical result really cemented their choice. The unbiased lower variance gradient from RLOO was key for reliable learning in this complex tool use setting.
Okay, so Arlo provides the stable engine. Now let's talk about the reward signal itself. We know simple token overlap like F1 doesn't work well. Can you maybe use the paper's examples to really illustrate why those traditional metrics are so misaligned with what we actually want, which is semantic correctness?
Yeah, the examples they give are quite telling. Let's take F1 score first. Remember, it measures token overlap. The paper gives an example, maybe asking for a specific date, like when was event X. Let's say the ground truth is July 8, 1945. If the agent answers June 8, 1945.
Almost identical, just one word off.
Exactly. The F1 score could be really high, maybe 80%, 90%, because 8, 1945, maybe names involved, all match. But the answer is factually dead wrong. The metric gives you a high reward for a false statement.
High score, 0 value. Got it. What about exact match? That sounds like it would fix the factual issue.
It tries to. By being super strict, the answer has to match the ground truth exactly, word for word. But it swings too far the other way. Imagine the question is, where was person Y born? And the ground truth is simple. Person Y was born in the United States. If the agent researches and finds more specific, accurate info and answers, person Y was born in New York, US?
Which is actually a better, more informative answer.
Right. Semantically correct, factually superior. But because it's not lexically identical to the simpler ground truth, the EM score is 0. The agent gets punished for being more accurate and informative. It's way too brittle.
So you're stuck between rewarding wrong answers with F1 or punishing correct but differently phrased answers with EM. Classic metric failure.
Precisely. And that's why they landed on AI feedback as the primary reward signal. They use a separate, powerful LLM. Think of it as an impartial judge to evaluate whether the agent's generated answer is semantically equivalent to the ground truth. Does it mean the same thing? Does it convey the correct facts, even if phrased differently?
So it's optimizing for meaning, not just words.
Exactly. Plus a small reward for correct formatting, but the bulk of the signal comes from that AI judge assessing semantic correctness. This makes it much harder for the agent to game the reward by just spitting out text that looks similar but is wrong. It has to actually understand and answer correctly.
Okay, so we have a stable learning algorithm, RLOO, and an aligned reward signal, RAI. Now let's bring in that final piece, the robust reasoning scaffold that operates at test time. You mentioned self-correction and self-verification. Can you clarify the difference in how they function again?
Sure. Self-correction is the immediate reactive mechanism. It happens during the research mode. A tool call fails bad syntax, empty results, whatever. Self-correction is the agent diagnosing that specific failure and trying to fix it on the fly, maybe by reformulating the API call or the search query so the research can continue without interruption. Self-verification, on the other hand, is that deliberate, separate step after an answer has been generated. It's not about fixing a single failed tool call. It's about reviewing the entire research process and the resulting answer for overall correctness, completeness, and logical consistency. It's a holistic check.
And you mentioned the paper had a great example with the Walter Scott question that really showed self-verification catching a subtle error. Walk us through that one again.
Yeah, it's a perfect illustration of that generation verification gap. The query was something like, in one of Walter Scott's Waverley novels, what was the heart of Midlothian? The agent did the research correctly. It found two key facts. One, the heart of Midlothian is the actual title of one of the Waverley novels, and two, the phrase refers to the old Tolbooth prison in Edinburgh. So far, so good. But when it first generated the answer in research mode, it kind of got lost in the details of the plot, talking about the main character, Jeannie Deans, and her journey. All factually correct information from the novel, but
It didn't directly answer the core question of what the heart of Midlothian was in the context of the prompt.
exactly, it failed to explicitly state the most obvious part. It's the novel's title. So the information was there, but the answer structure was flawed relative to the specific question asked.
So what happened when it hit verification mode?
The agent, reviewing its own work, flagged that first answer as incorrect, and its internal reasoning explicitly noted that it failed to state that the heart of Midlothian was the novel's title. Because of that self-identified structural flaw, verification failed.
And it went back to research mode.
Yep, cooked back into research mode. It then generated a revised, much more direct answer, clearly stating that it's the title and that it refers to the prison. Only then, when it went back through verification, did it pass and the thread completed successfully. It shows the verification isn't just checking facts, it's checking if the answer structurally satisfies the prompt.
That's a really powerful mechanism for ensuring reliability. Okay, but there's one more part to this scaffold. Research threads synthesis, RTS. This sounds computationally expensive running 4 parallel research threads. Why go to that length? When is this needed?
It's definitely resource intensive, and it's motivated by tackling the really hard, ambiguous problems. Think about complex research where maybe the evidence online is contradictory or the question requires synthesizing information from multiple very different sources. On those kinds of tasks, even a robust single thread might, just by chance or the sequence of its discoveries, follow a path that seems locally optimal but ends up converging on an answer that's plausible but subtly wrong or incomplete.
So running multiple threads is a way to hedge against getting stuck down one wrong path.
Essentially, yes. RTS introduces redundancy and a final reconciliation step. It launches 4, and hand 4 in the paper, independent research threads simultaneously. They all start with the same query, but because of the randomness in search results, slight variations in generated queries, etc., they'll likely explore different evidence and reasoning paths.
Okay, I have to push back here from an engineering standpoint. 4 threads means potentially 4 times the API calls, 4 times the LLM inference cost, and significantly higher latency. Is that trade-off really worth it? Is the accuracy gain from synthesizing these 4 threads substantial enough to justify that cost, especially for real-time systems?
That's the million-dollar question for anyone deploying this, isn't it?
Sure.
And the paper's results actually give us a pretty clear answer. It depends on the task. The RTS mechanism itself involves letting all 4 threads run their course. Then, the agent summarizes the key findings and reasoning from each thread. Finally, it performs a joint analysis across those 4 summaries to synthesize a single final answer that ideally represents the most well-supported conclusion across all lines of inquiry.
So it's designed for maximum accuracy and robustness on complex tasks, even if it costs more.
Precisely. It's a strategy for high-stakes situations where getting the most complete and verifiable answer matters more than getting a fast answer. The cost is acknowledged, but deemed necessary for pushing the frontier on the hardest problem.
That tees up the experimental results perfectly. Let's look at how PokeeResearch 7b actually performed. They compared it against other 7b open source models like R1 Searcher, Deep Researcher, right?
Yes, a suite of strong 7B baselines. And they tested it across a really broad range of benchmarks, 10 in total, all text-only versions. They grouped them nicely. You have your standard retrieval-focused QA, natural questions, NQ, trivia QA, TQ, Pop QA, Bamboo, BMB. Then you have the multi-hop reasoning tasks, which require connecting pieces of information. Hot-pot QA, Jiuqi multi-hop QA music. And finally, what they call the frontier or complex agent benchmarks. These are really challenging ones. GAIA, which mimics real-world tasks needing tool use. BrowseComp, specifically testing web navigation and information extraction. And Humanity's Last Exam, HLE, a tough general reasoning benchmark covering many domains. They report mean accuracy over 4 runs, mean at 4, judged by an external model for fairness.
And the headline result? How did PokeeResearch stack up?
The headline is pretty unambiguous. Both the standard PokeeResearch agent without RTS and the version with RTS, PokeeResearch RTS, achieve new state-of-the-art results across all 10 benchmarks among these 7B scale agents.
Wow, across the board. So that core combination of RLO training and the reasoning scaffold really does provide a fundamentally better base.
It absolutely clearly establishes a higher performance baseline. The stability from RLO and the reliability added by self-verification pay off consistently. But the really insightful part comes when you break down the numbers, especially looking at Table 1 and Figure 1 in the paper, and see where RTS makes the biggest difference. If you look specifically at those tough frontier benchmarks, GAIA, HLE, BrowseComp, that's where RTS delivers a really significant boost. On GIA, for instance, the standard PokeeResearch gets 36.9% accuracy, but PokeeResearch RTS jumps to 41.3%. That's a massive 4.4-point gain on a benchmark known for its real-world complexity.
And BrowseComp.
Even more dramatic there. Standard gets 5.4%, RTS pushes it to 8.4%. It's almost double the performance on a task purely about web competency. And on HLE, it goes from 15.2% to 17.6%.
So why is the gain so much larger on those specific complex benchmarks like GAIA and BrowseComp? What does that tell us?
It strongly confirms the hypothesis behind RTS.
Yeah.
These are exactly the kinds of tasks that involve multiple steps, ambiguity, potentially conflicting information scattered across the web, that require synthesizing divergent evidence. The fact that RTS provides the biggest lift here shows that reconciling those multiple independent research paths is crucial for finding the best answer when the information landscape is messy.
And conversely, on the simpler, more straightforward QA benchmarks, the impact of RTS is less pronounced.
Exactly. That supports your earlier point about the cost trade-off. On Trivia QA, the standard agent gets 91.3%, RTS gets 91.8%, a tiny bump. On Bamboogle, it's 74.5% versus 75.0%. Still slightly better, but the massive overhead of RTS yields diminishing returns here.
So the takeaway is, the core PokeeResearch system with RLOO and self-verification is already very strong, likely sufficient for many standard QA tasks. But for the really complex, ambiguous, high-stakes research queries, strategically deploying RTS, despite the cost, can unlock significant additional accuracy.
Precisely. It becomes an architectural choice based on the expected task difficulty and the required level of robustness. And we shouldn't forget the role of self-verification in that baseline strength either. The Walter Scott example showed it catching errors that simple metrics would miss. The overall performance isn't just from faster learning via RLOO, it's also from generating answers that meet that higher internal standard imposed by the scaffold.
Okay, let's wrap this up. To recap the key contributions from PokeeResearch 7B that we've discussed, we have this unified RL framework, the use of RLAIF specifically with the RLO algorithm for stable, unbiased alignment, especially critical in these sparse reward tool use settings. And then there's the robust reasoning scaffold, adding layers of reliability through self-correction, self-verification, and that strategic research thread synthesis for complex tasks.
And I think the results really hammer home the paper's main point. For building truly effective deep research agents, especially at manageable scales like 7B, the focus needs to shift towards reliability engineering and robust alignment mechanisms. It's not just about throwing more parameters at the problem anymore. There's specific design choices, stable, RLOO, the verification loop, optional synthesis deliver a remarkably capable and resilient agent without needing massive scale.
So for you, our listener, especially if you're working on building these kinds of autonomous systems, the clear message here is that the field is moving beyond basic metrics. We're now optimizing for verifiable semantic correctness and actively designing architectures to manage the inherent uncertainty and potential for divergence in complex research trajectories.
Exactly. And the paper kind of closes with this idea that PokeeResearch 7B is a stepping stone towards a future of autonomous agents that are not just capable, but genuinely verifiable. This leads to a final, maybe provocative thought for everyone to consider. Given the clear performance gains, especially on those frontier tasks, should mechanisms like explicit self-verification and maybe even thread synthesis become standard, required components in any production-grade research LLM.
Moving them from nice to have to must-haves.
Right. If we redefine what a complete answer generation process looks like to mandate these rigorous checks and balances, what does that mean for system design? We'd have to fundamentally rethink latency expectations, resource allocation. The engineering implications are huge if verification and reconciliation become as integral and potentially as resource-intensive as the initial information gathering itself. It suggests a future where proving the answer might be as important as finding it.